very good morning and welcome to this course on the foundations of continuum mechanics. Today we'll be discussing tutorial for week 7. So let us get started. The topics for today's tutorial are as follows. We will be solving problems from motion and deformation. We'll be discussing Lagrangian and Eulerian description problems, and we'll solve a couple of problems on material derivative. So let's solve the first problem. So as you see from the tutorial sheet from this week, this is the first problem. We are given the motion equations in their Lagrangian description, and we have to check whether this system is invertible or not. We don't have to invert it, we just have to check whether it is invertible or not. So for this case, we'll be using the idea of the Jacobian determinant. So we discussed in the lectures that a system which is represented by the transformation chi is invertible if the Jacobian determinant, that is J, is not equal to 0. In fact, we also said that from physical principles, J is always greater than equal to 0. So this condition has to be satisfied mathematically as well. Only then this system depicts something which is physical. And we can invert the motion as well. So let us write the expression for the Jacobian determinant. So the Jacobian or the Jacobian determinant is the determinant of this second order tensor small xi comma a, which basically is this determinant. So let us substitute the values for the different terms in this determinant. So the first term, which is del small x1 by del capital X1, can be found out from here, which simply becomes a 1. And I'll write all the other terms as well. So this is the determinant. And when we simplify this, and this can be simplified easily on this column. So when we do that, we get 1 times 1 minus 0, which is a 1. So since the Jacobian is greater than 0, so this means that this transformation or the motion function chi is invertible. So we can represent the capital X's in terms of small x's. Actually, this quantity small xi comma a is something we'll discuss in detail in the next 2 weeks, and this determinant being equal to 1 has a special meaning. But for right now, all we care about is the Jacobian being greater than 0. So since Jacobian is greater than 0, so that means this is invertible. Let us now go to the next problem. In this problem, the velocity field is given in its Lagrangian form, that is in terms of capital X's, and we have to integrate these equations to obtain small x as a function of capital X. That is, we have to find the motion equation from the velocity field. Some condition is given to us which will help us get the constants of integration, as we'll see. And once we find this, we have to find the velocity and acceleration components in the Eulerian form. So let's solve the problem. So we know that velocity field is defined as d by dt of the small x vector. And since small x is written in terms of capital X's, we can also write this as partial by partial t of small x, because it's a function of capital X in time. And capital X is not a function of time. So we can write this as only a partial derivative. So from this, we can find the small x's. In fact, this means v1 is partial by partial t of x1. So this gives us that x1 is integral v1 dt plus some constant c1. So let's solve this. So this is the expression we get for small x1. And similarly, we can find small x2 and small x3 as well. And these are the expressions for small x2 and small x3. Now we have to find these constants C1, C2 and C3, and for that we need a boundary or an initial condition, and the condition that's given to us is that at time equal to 0 the small x coincides with the capital X. That is, we have chosen the initial configuration as the reference configuration. So if we find x1 at t equal to 0, that becomes C1, x2 at t equal to 0. You just substitute t equal to 0 in the expression on the left. That gives us x2 plus c, and x3 at t equal to 0 becomes simply c3. And these are given to be capital X's. So that means this is capital X1, this is capital X2, and this is capital X3. So we have the expressions for the constants. C, this is C2. C2 becomes 0 from this. C2 is 0, and I'll box this. So when we substitute that, we get the expressions for small x vector in terms of capital X. So this here is the final expression for the motion. And this actually is the chi function because we are finding the small x's from capital X and t. So this completes the first part of the problem. The next part is that we have to compute the velocity and acceleration components in the Eulerian form. Now the velocity is already given to us in the Lagrangian form. So to convert that to the Eulerian form, we simply have to substitute capital X's in terms of small x's, which basically means we need this chi inverse transformation. And since we have chi, from here we can very easily find chi inverse because we only have x1 in this first, x2 in the second, and x3 in the third. It's straightforward. So this is the expression for our chi inverse. So we can substitute these in the velocity field that was given in the Lagrangian form. And when you do that, you get this final answer. And next we have to find the acceleration as well. We have to find acceleration in the Eulerian form. So acceleration is d by dt of the velocity. And if I express my velocity in the Lagrangian form, that is in terms of capital X and t, this becomes partial by partial t of velocity capital X comma t. So what we'll do is we'll use the Lagrangian form of the velocity that's given in the problem. We'll find acceleration. So this is a in the Lagrangian form, and then we will use capital X equals chi inverse of small x comma t in this acceleration to get the acceleration as a function of small x comma t. So I'll leave it to you to try it out yourself. Here's the third problem. So we have the velocity expressed in the Eulerian form, that is in terms of small x1, small x2 and small x3. This is the Eulerian form for the velocity field, and we have to determine the acceleration components at a given spatial location 1, 1, 0 when time is equal to 0. So till now what we have been doing is we've been writing acceleration as d by dt of velocity expressed in the Lagrangian form, which basically gives us the Lagrangian form of the acceleration. But eventually we need the Eulerian form because a spatial coordinate is given along with time. So we need acceleration as a function of small x in t. So what we have been doing is that first we find this Lagrangian form, and from here we find the Eulerian form by using our chi-inverse. So to get this chi-inverse, we'll have to first integrate these velocities, get the chi, invert it to get chi-inverse, substitute that in the acceleration here, and then proceed. That's a long process. We'll show you a shorter one. Let's understand what is the meaning of acceleration. So whenever we say acceleration, we talk about acceleration of a material particle, let's say p. So it's a body, a physical body whose acceleration we measure. It's all about acceleration for a given material particle p. So that gives us a hint that we are looking for the material derivative here. So acceleration is d by dt of the velocity, which in this case we're talking about so we're talking about the velocity of a particle capital Xp at t plus delta t minus the velocity of the same particle at time t divided by a delta t. So this is the acceleration that we mean here. So we are basically measuring the velocity of a particle that is moving. So we can see that we're looking for a material derivative here. So we can see that acceleration is a material derivative of the velocity field v. And since velocity is expressed in the Eulerian form, as it is the velocity of a fluid, and it is natural to express this in the Eulerian form, so we can write this as the sum of the local rate of change of the velocity and the convective rate of change like this. And if I express this in the initial notation, this becomes d by dt of some component of the velocity is equal to partial by partial t of that component plus Vk times del by del small xk of the same component Vi. Now, earlier when we discussed material derivative, these quantities were some nth order tensor. It just happens that in this case, they are the velocities. So the first component of acceleration becomes a1 equals del by del t of v1 plus v1 del by del x1 of v1 plus v2 del by del x2 of v2 plus v3 del by del x3 of, sorry, this has to be v1 and this is v1 as well. So now we substitute for the different components and the derivatives as required, and this will give us, so this is the expression for partial v1 by partial t, and this is the expression for v1 times partial by partial x1 v1, and this is the expression for v2 times partial by partial x2 v1. And the last one is simply 0 because v3 was given to be 0. So I'll write that this is the acceleration a1, the first component of that, in terms of x vector and time. This is a1 as a function of x vector and time. Now in the problem, it was given that we have to find the acceleration components for this particular spatial point at this time. So now we can substitute the value for small x vector and time. So now we substitute for 1, 1, 0 at time equals 0 as well. And this will give us the expression for acceleration of this point 110 at t equals 0, which is twice a times minus k plus 4a. So k and a are simply constants in this problem. Now, one thing we need to note here is that we only substitute for small x and t at the last step. The reason is because we had derivatives with respect to x and t. So we have to keep the expression general, and then in the final step we substitute for small x, particular, and particular time. Right, so similarly, I'll leave it to you again to find out a2 and a3 for this particular point 110 at time equal to 0. And if you do that correctly, you should get these values for a2, and a3 is going to be a 0. So this completes the third problem. So here's the fourth and the last problem from today's tutorial. The motion of a continuum is given to us, which is basically the chi function, and the temperature field theta of a body is given in terms of its spatial description, that is the Eulerian description. And we have to determine first the velocity field in spatial form, that is, we have to find v as a function of small x and t, and then using that we have to compute the material derivative, that is d theta by dt of the temperature field. So second is that we have to find d by dt of theta. So now that we're comfortable writing the material derivative, let's write it down. So this is equal to partial by partial t of theta. So this is Eulerian form, plus vk partial by partial xk of theta small x comma t. Now remember, this is for the Eulerian description only. If theta was given in the Lagrangian description, things would be very straightforward because we simply say partial by partial t of theta in the Lagrangian form. So it is in the Eulerian form that we have to apply this local plus convective parts. And for this, we need the velocity field, and that is the reason it is asked to first find the velocity field and then use the velocity field to calculate or evaluate the material derivative. So let us solve this problem. So first we'll find the velocity in the Lagrangian form, which is simply partial by partial t of small x written in terms of capital X and t. So this gives us v1 as partial by partial t of small x1 in terms of capital X and t. So using this, I can write this as minus x1 e to the minus t. Then v2 is partial by partial t of x2, which can be obtained using this. This becomes x2 e to the power of t, and v3 similarly is partial by partial t of x3, which is obtained using x3 expression, which becomes small x2 e to the power of minus t with a minus sign. Now this gives us the velocity in the Lagrangian description. And to get the velocity in the Eulerian description, we have to invert this chi function. And doing that is straightforward here. So let's do that. So from the first one, we get capital X1 is small x1 e to the power of t. From the second one, we get capital X2 is small x2 e to the power of minus t. And from the third one, now we already know capital X2, so we'll substitute that in the third. So we get small x3 is capital X3 plus x2 e to the power of minus t times e to the power of minus t minus 1. we'll simplify this. I'll move x3 on the left. So x3 becomes small x3 minus x2 e to the minus t times e to the minus t minus 1. So this simplifies to x2 e to the power of minus 2t plus x2 e to the power of minus t. So this is the expression for x3, and these are the expressions for x1 and x2. So these three collectively give us the function chi inverse that we have just obtained. Alright, so now we have everything we need. We can substitute these, let's call these 1, 2 and 3 into the expressions for the velocity. So we substitute from 1 to 3 in above, and this will give us v1 this time as a function of small x and t, which becomes simply minus x1, v2 which is a function of small x and t becomes small x2 times e to the minus t, and similarly v3 becomes minus x2 e to the power of minus 2t. So this is the Eulerian description of the velocity field. Great. So we have what we needed for part 1, and now we'll move on to the next part to find the material derivative of theta. So d theta by dt, the material derivative of theta, where theta is written in the Eulerian description, is partial theta by partial t plus vk del by del xk of theta, written in the Eulerian description. Now remember, these vk's are also in the Eulerian description, so that we get the expression overall in the Eulerian description. And we have got these vk's now. So let's substitute these. Now the expression for theta, let's quickly have a look at it, is this. So let's copy it. So partial theta by partial t becomes, there's only this term that has a t. This becomes a minus e to the minus t times x1 minus 2x2 plus 3x3. So that's term number A. Let's call this A. And then this is B. So B is a sum where we have v1 del by del x1 theta plus v2 del by del x2 theta plus v3 del by del x3 of theta. So v1, as we just found out, was simply minus x1, and if you differentiate partially the theta with respect to x1, this becomes e to the minus t times a 1. Then we have the second term, which is v2. So v2 was x2, and del theta by del x2 is simply e to the power of minus t times a minus 2. And then v3, which was minus x2 e to the power of minus 2t times e to the power of minus t times a 3. So let us simplify this expression. I'll take e to the minus t common. So that will give me a minus x1 minus 2x2 minus 3x2 times e to the power of minus 2t. So we have a and b now. So we can find the overall material derivative as the sum of A and B. So this completes the problem where we had to find the material derivative of temperature theta in its Eulerian description. So let us summarize the tutorial now. So today we solved 4 problems. These problems covered the topics on motion and deformation, written both in the Lagrangian and the Eulerian descriptions, and 2 problems on material derivative. So in the first problem, we applied the idea of Jacobian determinant to identify whether an inverse mapping exists or not. In the second problem, we integrated the velocity expression given in the Lagrangian form to get the expression for motion, that is the chi function. And from that, we found out the velocity and acceleration fields in the Eulerian form. The third problem was quite interesting because we found out the acceleration in the Eulerian description using velocity in the Eulerian description by using the idea of the material derivative. We didn't have to go to Lagrangian form and then use the chi-inverse to get the Eulerian form from that. We simply could differentiate the velocity field, which acts like any other tensor field, using the idea of material derivative. And in the fourth problem, we again applied the idea of material derivative to find the time rate change of the temperature field, which was given in the Eulerian description. So after solving these 4 problems, I'm sure you have got some confidence in terms of working with the equations of motion, that is the transformation from material to spatial and spatial to material coordinates, and then work with quantities which are expressed in either their Lagrangian or the material form or the Eulerian or the spatial form. So we end the tutorial now, and in the next week, we jump into the world of strain. Thank you very much, and I'll see you in the next lecture.